Okay, good morning, ladies and gentlemen. Today I'm going to talk about our recent work on the software-based live migration for RDMA. And this is a joint work by Tsinghua University and Microsoft Research Asia. So live migration is moving running services from one host to another with minimal disruption. Thus, it is critical to server upgrades, maintenance, and load balancing in modern data centers. And typically, migration source first pre-copy some states, like memory, to the migration destination, while the services to be migrated are still running. Then the live migration tools perform stop and copy to migrate the states. And after the restoration, some states are transferred during the post-copy. So when the service needs the states that are absent on the migration destination, the live migration tools will fetch from the migration source. So during the entire workflow, the services are completely unavailable during the stop and copy, and this duration is called the blackout time. And during the pre-copy and the post-copy, the services are available, but with performance declines, and this duration is called the brownout time. So the goals of the live migration is to minimize the blackout time and reduce the impacts of brownout. And in recent years, we have seen a wide deployment of RDMA in data centers. RDMA offers high throughput, ultra-low latency, and high CPU efficiency. Thus, it has been widely adopted by major cloud providers to boost the performance of applications such as machine learning, graph computing, and distributed storage. However, modern data centers do not support RDMA live migration. The main reason is that most communication states are managed by the RNICs, and there is no interface to migrate these states. This is very different from the live migration of the TCP/IP. For the TCP/IP of virtual machines, the communication states are within the network stack of the guest OS. So as long as we restore the guest OS, the communication states are alive again. For the TCP/IP in container scenarios, the Linux kernel has introduced the TCP repair to allow the live migration tools to fetch the socket states from outside the processes and inject these states to the new sockets created on the migration destination, and the live migration is transparent to the applications. So as the communication states are within the software for the TCP/IP, the live migration of TCP/IP is very easy. A recent work for the RDMA live migration introduces a mechanism similar to the TCP repair inside the RNICs. And besides, it extends the Rocky V2 protocol to explicitly notify the partners that their peers has changed to another location. And this solution requires the hardware changes, and it is not readily deployable in modern data centers. So our motivation is to establish new RDMA communications on the migration destination and introduce a software indirection layer to hide the changes. And our solution does not require any changes to the existing RNICs. However, offering software-based solutions to support RDMA live migration faces the following challenges. First, setting up the RDMA communications is very slow. So establishing the communication during the stop and copy is unacceptable because the blackout time may be long. Thus, we need to pre-set up the RDMA communications during the memory pre-copy. However, the challenge lies in the registering the MRs during the memory pre-copy. So after live migration, although the physical memory address may change, we need to keep the virtual memory address the same for the transparency concerns. However, on the migration destination during the memory pre-copy, the virtual memory addresses may be different from the application's original virtual address. This is because for the convenience of the restoration, the live migration tool will allocate a large continuous memory to restore the contents, and then remaps them one by one to the application's original virtual address. So at this time, we cannot register the MRs using the original virtual address because there is no corresponding physical address at this time. And second, many communication states are managed by the RNICs and exposed to the user space. These states include the QPNs and MRs access keys. They are used at each time of the data path operations, which bypasses the kernel. And the live migration tools cannot control the assignment of the QPNs and the access keys. So we need a lightweight indirection layer to hide the changes. As the RDMA bypasses the kernel, it is very hard to add such an indirection layer. And besides, for one-sided operations, applications need to get the remote access keys from the remote side. So it is even more challenging to hide the differences from the communication partners. And finally, even the services are frozen at stop and copy. The RNICs will still continue operating the messages. There's no way of stopping all the connections immediately, and the states of the in-flight work requests cannot be accessed from the software. So it is challenging to handle the consistency issue. And even worse, the migrated service is unaware of the one-sided verbs issued by the partners. So it is even more challenging to preserve the work request consistency. So in this work, we propose migration RDMA. Migration RDMA is a software-based RDMA live migration solution. We propose 3 main ideas to tackle the challenges. First, in the RDMA driver, we provide efficient virtualization of the RDMA states. We map the translation table into the RDMA library. And second, during the memory pre-copy, we modify the memory restoration workflows to support registering the MRs during the pre-copy. And third, at the start of the stop and copy, we suspend the RDMA communication to prevent further work requests, and then wait for all the in-flight work requests to be completed. Now let's dive into the 3 ideas in details. So for registering the MRs during the partial restore, we first restore all the memory structures at the start of the restoration. As such, we can register the MRs using the original memory, virtual memory addresses. Then we start the rest of the memory restoration. And during the pre-copy, the migration source may register new MRs. These new MRs may be conflict with the intermediate memory structure used by the live migration tool. Thus, we need to delay restoring these MRs to the end of the memory restoration. And in terms of hiding differences between the source and destination, the key point is to virtualize the QPN and access keys. For local QPN, the translation happens on 2 directions. So for one direction, when applications post work requests, the migration RDMA library needs to translate the virtual QPN to the physical QPN, and then passes the physical QPN to the RNIC. And when the RNIC generates CQ entries to notify the applications, the migration RDMA lib needs to translate the physical QPN inside a CQ entry back to the virtual QPN. So we maintain a global translation table from the physical QPN to the virtual one in the migration RDMA driver. This translation table is shared by all the migration RDMA lib through the memory mapping. And in terms of the local access key, we also maintain the translation table inside the migration RDMA driver and use the memory mapping to share with the RDMA library. For efficient translation, first, the translation table is maintained on a per process granularity. And the second, we store the translation table closely together as an arrays. The arrays index is the virtual local access key, and the corresponding value is the physical local access key. So in terms, for the remote access key and the QPNs, the migration RDMA library maintains the translation table for each remote process. The translation table are all invalidated at first. And for the first time of the translation, the migration RDMA library fetches the corresponding mapping remotely and then catches it locally. So the subsequent translation of the same remote QPN or the remote access key does not need extra communication. And when the live migration occurs, we invalidate the corresponding mapping cached on the partner side. So after the migration, after restoration of the services, the partner will fetch a new mapping. So finally, we need to handle the in-flight work request consistency. So far, we have considered 2 methods to conduct consistency. One is wait before stop. It is waiting for all the work requests to be completed before freezing the services. And the second one is drop and replay. So we've dropped all the work requests at the migration source, and then finally replace all of them on a new location. And after comparison, we find that replaying all the work requests takes a similar time to waiting for all the work request completion, because their bottleneck both lies in the network bandwidth. And besides, discarding all the on-the-wire work requests is time-consuming. The typical method of discarding all the work requests is resetting the QPs or destroying the QPs. However, resetting or destroying all the QPs is very slow. So we finally choose the wait before stop to handle the consistency issues. The key point of the wait before stop is that we need to ensure the applications can still execute during the wait before stop. So we suspend the QPs to prevent further work requests. And for the new work request, the migration RDMA library will intercept the work request and directly returns to the applications. So the applications will not be blocked by the suspended communication. And what application sees is that it had posted the work request to the RNX, but got the CQ entries slower than before. And for the in-flight work request, we spawn another thread to poll the CQs for applications. And to ensure applications can poll the CQ as normal, we maintain a fake CQ for each real CQ. The fake CQ is actually denoted by the Q pointer, and applications poll the fake CQs during the wait before stop. And after the restoration, the migration RDMA posts all the intercept work requests. And besides, applications continue polling the fake CQ until it becomes the empty. And finally, we destroy the fake CQs and poll the real CQ as normal. So our implementation is mainly targeted for the container scenarios. We have modified the OIVD driver, the CRIU, and the runC. And our evaluation testbed consists of 6 servers, 1 as a migration source, 1 as migration destination, and 4 as partners. They are connected through the 100 Gbps RNX. So firstly, we evaluate the benefit of the RDMA preset hub by comparing the blackout time of the migration RDMA with and without the preset hub. For the without preset hub case, the blackout time is very long. And the time of restoring the RDMA takes a lot of time. This is because establishing all the communication is very slow. Adopting the RDMA preset hub can reduce the blackout time by up to 58%. But actually, we cannot get more gain because the CRIU is not very efficient to support the live migration. And besides, we did not conduct any memory pre-copy by the time we submit our paper. And second, we evaluate the overhead of the wait before stop. From the evaluation results, we can see that the overhead is relatively small. It is mainly bottlenecked by the transmitting time of the in-flight messages over the network. And thirdly, we evaluate the performance implication. And first, we evaluate how much overhead our indirection layer incurs in the data path. The evaluation results show that it only incurs 3% to 9% actual CPU overhead. And next, we evaluate the real-time throughput during the application's runtime, and among which we conduct live migration. The results show that migration RDMA incurs negligible performance implication experienced by the application, and the brownout has little effect. And finally, we conduct evaluation on the RDMA-based Hadoop. The baseline means that the Hadoop runs to completion without any live migration. And failover means that we destroy an original task and restart the task on a new server. The evaluation shows that migrating Hadoop using the migration RDMA does not incur too much extra time or severe performance declines. So in conclusion, migration RDMA is the first software-based RDMA live migration solution. It mainly proposed three key design ideas to tackle the 3 main challenges, and evaluations demonstrate low extra migration time and a low virtualization overhead. And currently, our prototype it has been open sourced. And thank you for listening, and please feel free to ask any questions.
Great talk. And we have time for a couple of questions. Okay, maybe while we're waiting, let me start with one question. Sorry, yeah, can I ask a question? So I love the work because I think, really ingenuity to make it work using today's hardware. Looking forward, you expect that you're gonna also potentially change the hardware in order to make it easier, or you think this is gonna be a solution that can also serve for many generations?
Okay, can you repeat that?
Sorry?
I didn't fully understand.
I'm saying, so this is a great solution because you don't need to change the hardware, so it can be deployed today. In the future, you expect this solution to also serve for many generations, or you expect, the hardware will change for
Okay, in the future, we expect that so the solution will not very heavily rely on the hardware, because deploying the solution in the hardware is, I think it requires many engineering effort. Doing this work, we are exploring that can we do most of the work in the software. Maybe in the future, I think that there's some works that some feature of the live migration that requires the hardware, but I think with the help of our work, the hardware will not become very heavy in the future. Okay.
Super, really exciting. Any more questions? If not, I guess in terms of time, we can move to the next session. And of course, you can catch up with the speaker during the coffee break. Let's thank the speaker again.